Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to introduce the topic of entropy. And entropy is a measure of disorder. So if we're talking about a student's messy bedroom where everything's chaotic, we would say that that bedroom has a lot of disorder or a lot of entropy. However, if you're very tidy and very neat and you keep your room very organized, okay, we would say that that bedroom would have a low entropy because there's not a lot of disorder. Now, if you're in kind of like an introductory college class or you're in an AP chemistry class, they like to talk about disorder as terms of microstates, the amount of positions available for that item, so to speak, okay? So microstates, if you're a little bit more advanced, disorder, if you're just in a regular chemistry class, honors chemistry. Even I talk about this in the AP class, but I do like to introduce this idea of microstates if we're talking AP chemistry or college chemistry, okay? So when it comes to entropy, okay, the molecular arrangement, okay, matters, okay? So solid, liquids, and gases have different molecular arrangements, okay? In a solid, all the molecules are packed together. In a liquid, they start to slide past each other. In a gas, they're very far apart from each other, and if they ever come close to each other and collide, they're just going to bounce off and get far apart again, okay? So when it comes to entropy, okay, which is a measure of disorder, solids, liquids, and gases have very different entropies or the amount of disorder in them. If we take a look at this solid and we look at this molecular arrangement, it looks like everything has its place. Everything is locked in, okay? They can't slide past each other. They can't have a lot of different places or microstates, okay? They're kind of like locked into place, okay? So for solids, we tend to say that they have a low entropy. And that's because everything is locked in and everything's in a particular place, okay? Now, I do want to talk about solids in a little bit more detail because solids, even though they're kind of locked in place, they are still moving, okay? So solids, they will vibrate against each other, okay? So you have this type of motion, and you also have rotational motion, okay? So there is movement in a solid, okay? So we're not going to say they have zero entropy. We're just going to say they have low entropy. Now, the way you get from a solid to a liquid is you actually supply heat. And if we're able to supply heat, we're able to get these, to break these intermolecular forces, and we're able to get the molecules to start to slide past each other. Like this molecule here, it's been opened up enough so these molecules can start sliding past each other. And if they can slide past each other, well, there's more positions or microstates that they can get into, okay? And there can be more randomness, okay? And therefore, there's a little bit more disorder with a liquid versus a solid because of the positions that they can get into, okay? So we would say that a liquid has what I would call medium entropy. So we're very kind of like qualitative here. We're not putting exact numbers on anything quite yet. We will do that in a few lessons, okay? And of course, if we keep adding some heat energy, we can get these liquids to heat up enough to where they get really far apart from each other, and then they're just bouncing all over the place. It is super chaotic. It is super disordered. There's lots of microstates that they can be in per second, okay? And therefore, we're going to say a gas has very high entropy, okay? And with knowing the entropies and their molecular arrangement, we kind of get this graph to come out, okay? So as the temperature increases, okay, we're at a solid, and this would be 0K. So at 0K, 0 Kelvin, there's no entropy because we removed all the energy, and the vibrations and the rotations cease to happen, and everything lines up in perfect order or zero entropy at 0K. But as soon as we get to 1K, which is negative 272 degrees Celsius, which is super cold, there's at least some entropy, there's some vibration, some rotation, and as the temperature increases, those vibrations and rotations start to happen more and more to the point where we're going to have melting occur. And when melting occurs, when we go from solid to liquid, there's going to be this big jump in entropy, okay? And now that we're at a liquid, okay, as we heat it up, we can make that liquid kind of move faster and faster, and therefore the entropy is going to increase. And if we keep adding some heat, we will vaporize it into a gas. So in the transition from liquid to gas, okay, there's another humongous jump in entropy, okay? So, and that jump is going to be larger than the jump between solid and liquid. So the liquid to gas entropy change is going to be larger than the solid to liquid. And that has to deal with the molecular arrangement. Remember, solid to liquid, you just have to open it up just enough so that they slide past each other. To go from liquid to gas, from here to here, you got to get these molecules really far apart from each other, okay? So, and when that happens, you'll have this humongous change in entropy value. And of course, as we heat the gas a little bit more, it even gets more entropy. So there's a few bullet points that we have to get out of this graph, okay? Bullet point 1, okay, is that you can have zero entropy only at 0K. It's the only time that you can have zero entropy. As long as you have 1 Kelvin, you're going to have some level of entropy. And in thermodynamics, a lot of times we like to talk about at 25 degrees Celsius, which is room temperature. So most of the time we're going to be above 0K, so we're going to have at least some entropy, okay? And then so the next thing, okay, as temperature increases, as temperature goes up, entropy increases. So that's a direct relationship. So as this temperature goes up, the entropy goes up, okay? And then the next bullet point is you're going to have these big jumps in entropy with state changes, okay? So we're going to say that the entropy change will be really big, okay, with state changes. I think we get, so when we go from solid to liquid, there's a big jump, and when we go from liquid to gas, there's another big jump. And then the last bullet point is talking about the jumps between liquid and gas versus solids and liquids, okay? And that is when you go from a liquid to a gas, okay, the entropy change is much larger than solid to liquid, okay? So liquid to gas, okay, the entropy change is much larger than when we go from solid to liquid, okay? So this change is much bigger than this change, okay? And that's kind of like what we should get out of this graph, okay? Now, what we're going to take a look at is we're going to take a look at this chart that I have over here and talking about entropies of substances. So we're not talking about entropy change. We're just talking about the entropy of a particular substance, okay? Now, if we use these bullet points here that we have up here, we can see that some of these things are possible, okay? Now, we're going to say that everything over here is going to be at 25 degrees Celsius, at room temperature, okay? So we don't really have to pay attention too much to this first bullet point, okay? Or the second bullet point, because it's talking about as temperature increases, okay? But we do want to talk about these entropy changes that happen with state changes, because everything up here at the top is a gas. In the middle, I got 3 things that are liquid. In the bottom, I have 3 things that are as a solid, okay? If we look at the values for solids, okay, in general, if we had to average this out and average this out and average this out, that the solid would have the lowest average, the gas would have the highest average, and the liquids had to have the you know, kind of like in the middle, okay? Kind of like what we're talking about with here, low entropy, medium entropy, and high entropy. But as you investigate this a little bit further, you're going to find out that there's going to be other factors, okay? So when you're trying to figure out the entropy of a particular substance, the first thing that you should look at is solid, liquids, and gases, okay? That will give you an indication, okay? And I have 2 substances that are exactly the same. I got this CH3OH, okay, as a gas versus a liquid. And as a gas, it's 237, and as a liquid, it's 126, okay? So you have these big entropy changes, okay, with these states of matter. So first thing that I always look at for the entropy of a substance, is it a solid, is it a liquid, or is it a gas, okay? And then from there, I have to look at and analyze a little bit more detail because of these solids, okay, we know that they're the lowest, but some of them are lower than the others. Like this FeCl3 is much higher than these individual elements, and the NaCl is higher than these individual elements. So it looks like the number of atoms and the molar mass contribute to entropy. So I think that's a bullet point that we need to include in here, is that the number of atoms and molar mass contribute to entropy. So it's not just solid liquids and gases, it's also the molar mass. So of all the solids, you can see the one with the highest entropy is 142.3, and that's because the molar mass of iron is really large, especially when you combine it with 3 chlorines. That could be more than an H2 that's in the gas phase, okay? So you do have to take these into consideration as well. So it's a combination of solid liquids and gases and molar masses, okay? But of the gases, the one that's the highest, okay, is going to be the one with the most atoms and the one that has the largest molar mass, okay? And if you want to just go atom to atoms, there's 2 atoms here and 2 atoms here for a molecule of each H2 and N2. The one that's higher is going to be the one with the larger molar mass, okay? So just wanted to introduce entropy to you guys, okay? In the next video, we're going to talk about entropy changes and predicting if a chemical reaction has a positive or negative entropy change, okay? So this video just introduces entropy, and then the next series of videos is going to talk about entropy changes. And if you found this content helpful, please give it a like and subscribe.